Hello, so let me start. Morning, I did not bring this torch cell, which is what is the basis for the design you are seeing there. Basis for the design is the torch cell that is here. So, if you see here any of these designs is based on a physical reality. Physical reality is in this case is the diameter, then the what you call height, and then there is a small knob like thing at the bottom. This is where what you call a lot of specialties or I am sorry, reality check has to be done. Depending on the devices for which you are designing, you need to take the original. If you see this cap here, the so called AA cell was probably around 2 inches at one time and half an inch. So, I have 12.7 and then 50.5 and so on like that, 50.8, okay, 51. Now, you see the small detail at the top is very critical for us to proceed to the next slide. So, you must have this real thing as from the final batch which they are going to supply. Only issue being is often there is mild variation from batch to batch and what the manufacturer has contracted in his manual. So, you need to have the original data which is in the manual and the actual pieces here. Now, please look at my what do you call thing there. Just to make you, I will try to make this brief. If you remember, we started here saying I started with a cross section, okay. Somewhere here the original profile of this from left to right is there, and then as part of this profile I have a thickness here, I have a small ridge like thing here, ridge here, and something you will notice is that we have a very different thickness here and a different thickness here. So, what do we do about those thicknesses and how did we come about it? Now, this thing needs a something to close itself also on top of it. Please look at this. I have this box which is meant for my hearing aid, and you see the profile, they have made some small dent so that a spare battery can be kept there, spare cell can be kept there. Right now, of course, this is meant for a bigger thing. So, if I take this, it is supposed to go here, go back here, and more important is when you close it, it should close and probably snap. So, I have a catch here, I press the catch and it releases and goes back, and you see little more detail about the hinge. Can you see? When you take it out, the hinge is here, it is not here, hinge is here, and then there is a tremendous mechanism is here, and it completely it swings itself out of the way. This is where I feel our rapid prototyping probably helps. Can you see here, there is a small hinge that is part of it, and you need to develop the whole thing from the various the space I have shown you there. So, though the starting point is the same cell, you see the amount of what do you call thing which has gone into place. Okay. At this point, allow me to what do you call get back to something which is more interesting to hold your interest. Now, how does the machine, the what do you call filament deposition machine, how does it build these things? Because everything seems to be critical about how it builds. So, for your I mean for I am sorry for saying it, for your I will say for my benefit, look at the cross section. So, what I am going to do here is right now remove parts of the material coming from top and see how just what you call pay attention and stay with me for a short time. This is how the layup is going to start. For convenience sake, I have just removed all the top portion of the material, and then by a little bit of what you call interest and a little more of little bit of intention, little more by accident, you see that back thing has remained as it is. So, as the layup starts, that what you call that nozzle is going to fill material like this slowly depending on the type of algorithm they have. Some of them go diagonally like this in one layer, some of them go straight away like this. So, when I do undo it, first layup is going to be this much. The bottom portion is being built slowly. So, whatever thickness is, in this case for convenience and speed, I have just removed the top. This is how the layup is going to start. And now, when you go to the next what I call feature, I will just undo it here and then try to show you the next feature. You see here at the top, see what has happened. Those small things including that dividers between the what they call the cells, then the left and right things, and then the front and back, they are being slowly built up. This is where I wanted to tell you we have three axes, x and y and z. X and y, those things depend tremendously on the basic resolution of it and the nozzle characteristics and so on. The z or the vertical axis, the slices depending on the complexity of the machine and the build of the machine and so on, they may or may not have the same type of resolution of the other things. So, the first one, the base has been built. After that, part of the ribs have been built. Now, I will again undo it and show you. See, if you see a little closer, part of the taper is being built. In this case, I have intentionally chosen half the taper. So, see here slowly that tapered section is being built. This is one thing which what I call is very much characteristic of any of these things, which is a layup type of things which has a distinct physical thickness. In that it cannot form a smooth plane as we think it is. So, you get something which is slightly jagged. Jagged means you have, depending on the thickness and depending the overlap and depending on the rate of heating and rate of cooling and all that, this slowly starts building up like this. The bottom first layer was the base. Probably it could be made out of, depending on a thickness, suppose it is a 1 mm thickness and the resolution is around 0.2 mm, usually they will have 5 to 6 what you call runs on that to build up that 1 mm, and then later on they will build the ribs. Ribs, starting from the ribs onwards, the algorithm which is used for moving it, algorithm is a very, I mean what you call too general and too abstract a way. The path which the nozzle takes will be different. Advantages, because there is material here, there is no point in that nozzle going everywhere here. So, logically probably the nozzle moves one length and then moves over to that and moves and so on, depending on the manufacturer's capability and so on, and the type of what do you call the technology at that moment, they will make an optimized way out of which of building these things. So, no material is deposited here. However, material was there and this next layer, it needs to now follow up, and getting this corner is a tough job, where the difference between novice made at home and the professional things helps. All these professional things, that nozzle which builds, it knows how to move here, it knows how to move here and how to maintain this corner sharpness. But in spite of it, occasionally we have a chances of things being what they call built properly and improperly, little bit of errors. See here, I have come back here. Now, I will move it to the next higher level. Intentionally I have taken it there so that you can see a little bit of it, and then I will try to remove the You see here, for the first time, you will notice that whatever features we wanted to are being built up gradually. Good point is that the sharp portion has been completed already, the sharp portion here. This is where what you call, depending on your application and depending on the sort of hype you have come about, if somebody says I can make a knife using rapid prototyping and I can smuggle it in and all that, no, you believe him, don't unnecessarily argue with it. It's still, a lot of it depends on how well that what you call pyramidal that corner, no, has been built. Is it sharp enough? Does it have a Gothic arch? Is it straight, or does it have an what do you call the inverse hyperbola type of things? And the profile is the one, no, it makes lot of difference which you can do depending on the type of machine and the material. You can play with it a lot. In this case only for a sample I have made, so I have just said triangular thing. But you see here, what I feel is equally important thing is, you see how well the circular features are being built. Is an advantage and a disadvantage. Advantage being anything you want can be made, disadvantage being the detail is an important thing. And maybe in the next class and maybe after demonstration, I would like to show you whenever there is a void or a space, I mean pay attention again, whenever there is a void or a space, something called a support material is built up. The earlier machines, they had a different support material which is made with polylactic acid. So polylactic acid is something which has a melting point which is a at least 10 degrees lower than the base material. So this whole thing is put in a hot water bath and sometimes left to soak overnight or sometimes a few hours, and afterwards you need to snap off that part of the support material such that you don't need to have it in the original thing. The new ones are slightly improved on that, because printing a support material and again changing all that in spaces like this is a little problem. You see here, if you see the space here, you want to now fill a support material and try to fill it, life is not that easy. So depending on the machine you want to use and depending on the facilities, you may have to modify the undercuts and these things. Now I will go back here again. Now I will raise it to the next higher level. Right now it is here, part of the thing has been built, if you remember. That is approximately half the diameter of the circular spaces which I wanted to include. See here, several features you are able to notice. One of the features you are able to notice is that as the things build up, at this point this angle is almost 90 degrees, and if you see the cross section here, small details are features here which you can either improve, make use of it, try to do whatever you want. In this case, I want to have an electrical connection in it which is not visible outside. Understand? No, I need one electrical continuity. Typically, if you have a what do you call a spring here, and then if you have I am having a spring here, and if you have a simple contact here, and if I want to join it here, it is possible for me to add certain of these things at this point. So in the original model, if I now create a space in which an electrical wire can be installed, it's possible for me to, at least in some of the machines, to stop the machine and add the inserts as I like. In case that is not possible, we can probably make a through hole here and then try to do whatever operations we want to do. You have got this point. At this point, in case I want to join anything, no, make a wire, make anything, or in some places now I have even seen concealed printed wired boards installed into these things, which is not possible in a conventional injection molding machine for the rate at which you are able to do this. So, it is possible for me to stop and then put a what you call groove like thing, build it up with material, but you have to be very careful, because not all machines know the what you call the machine inside does not sense the put something here. So, you need to be very careful. I will give you a secret. We have, it's a more in what you call more nice story to tell, and very rarely we have been actually successful in making it like this. Okay. Now, I will continue with the building and see. You will notice now slowly that hole, the circular feature is getting completed, rather it is being closed. Now, at this point is where only your experience will teach you how far you are nearer the intended object, and then what you need to do with it. Do we need a space here? Do we need a hole here? And can we make any of these openings later? Can we have a second operation? If you want to have a second operation, very much possible for you to make a small dimple or a small opening here, so that it is possible for you to enlarge it. Marking is already there. You can use probably a drill bit or a hand this thing, and including, depending on the taps you have, can we tap a hole? In earlier things, it was not easy to build such things like what you call threads and threaded fasteners. Right now, depending on the granularity and all, threaded fasteners also can be built. Alternately, if you have taps which have a coarse pitch, it is possible to leave a pilot hole and continue the tapping later. So, I will just sort of, I want you to have a look at how this is. Now, you see, so far we have come. You have seen that I started with a base by which only the base portion of it has been built. After that, these ridges in 2 or 3 steps, these ridges have been built. Now, I have shown you where to stop in the middle. Now, I am showing you where it is around 45 degrees, that whole thing is covered in this. You have seen this? Now, I will now go back again, undo the what you call boolean I have done, and then see next level. Now, I will go to the next level. Oh, I am sorry. If you see here now, practically most of it is ready with a little bit of material left here. So, because we were in the learning phase earlier, we will not stop the machine, but carefully observe whether this portion has been bridged or not. Because we have found out, especially when support material is there and all that, now we had a little bit of problem with this bridging, and very rarely perfectly circular openings were possible to be done. So, we will usually compensate it by having something which is maybe around 0.3 mm opening smaller, and then after that use a plug with a emery, what we call this. You have seen this emery which is used for painting, zero emery, and then try to smoothen it, put it inside and try to smoothen it after the operation is over. So, we used to observe this carefully, and it is easy for us now I will continue with the, I will go back again, remove this top portion completely. Now you see this is the full thing has been built, easy enough, is it not? So, this is the first starting thing which we have started with. Now, I would like to come to saying what if I wanted a cap to be built on this. I need a cap and it should be snap fit, or I should have a what do you call a snap or a catch similar to what you have on these various types of, in this I have got a latch here, can we do it? This, because it was a starting point, I did not go further. Now, I will do one thing, for me to make things easy, I will just create a cutting plane for this object. Sorry, wrong direction. Some of the advanced modelers you can directly do, for example, solid and SolidWorks allow you to do this. In this case, this is a primitive what do you call more than primitive what do you call free off the net type of a. So, here what I do, I will do a Boolean difference from this object. Oh, sorry, complete bomb, yeah. Yeah, got it finally. See, this incidentally is the cross section of the object. If I want to now create a cap for it, it is very easy for me. All I need to do is